Yeah, is it visible?
Yeah, it is visible. We are now live, we can start.
Okay. So in this tutorial, actually, I'll be going to discuss about the ontological models of quantum theory and some of the fundamental results that has been came out in last few years. So it is actually a growing topic, and I want that you should interact with me while I'm discussing all these things. So let it not be a tutorial, but it is a like a interactive session. So by doing so, we will learn something about these ontological models and all.
Yeah, from our side, we will also request the participants to please interact, because quantum foundations and all these things have lots of jargons. So it's better that you understand meaning of each term and each word. And so I also hope that you'll go slow.
Yeah, sure.
Yeah.
So my screen was out, right?
Yeah, we can see your screen.
So now I'm again sharing this.
Yeah.
Okay, now you can see, right?
Yes.
Okay. And any point of time, you can just stop me and ask questions. Like, don't be shy and don't think that any question is a silly question. Okay. So every question has a meaning. Okay. So let us start with a very basic example. You even don't need to know very deep into quantum mechanics to understand this. Only you have to know the superposition of in quantum mechanics, superposition principle. So let us consider this example, like a coin toss example. Like I have given you a coin and you toss it. So there are only two outcomes, like head and tail. So like I am giving you a coin, and then I will provide all the parameters. You toss the coin, I will provide you all the parameters, like the initial position of the coin in your hand, then the velocity of air, then gravitational force, and any other parameter or any other variables that you may have in this scenario. I will provide all these parameters. And now you toss the coin, and if I ask you that, can you tell me where or what will be the outcome of the coin toss, like whether it will be a head or tail? So if you are aware of Newtonian mechanics, then you and you can do a certain calculation. So from Newtonian mechanics, by just by formulating some equation, you can exactly predict what will be the outcome of this coin toss. Yeah. So this parameter, if the parameters are provided, like this frictional force and this air motion and this gravitational force and any other thing. So now, so that means you have certain equations, certain theory with which you can predict definitely the outcome of some event. Okay. And if I also ask you that, can you tell that at a certain point, what will be the position or what will be the angle it will make with the perpendicular axis, you can also tell that by using the same equation of motion, right? So you have a event by event description of certain events in your classical worldview, like whatever we see in our classical world from our childhood. And that all of that are actually predicted by some kind of laws. We say that these are Newtonian laws and also classical electromagnetism. Like if I go to like how fan is moving or something like that. So that all are coming from Maxwell's equation and all. So classical electromagnetism and these Newtonian laws of gravitation and normal laws. So from those things, you can describe your observation that are going on in this world. But now let us consider this one. So actually quantum mechanics, the birth of quantum mechanics is because of that certain kind of microscopic phenomena was not explainable by these existing theories. So that is why this observation that are going on in this world. Hello. Oh, okay. So okay. So can you see my screen?
Sure, we can.
What is going on?
What happened?
Okay, it's coming. So now consider another example, that is I am taking from quantum mechanics. So you all know about this Stern-Gerlach magnet. So in the Stern-Gerlach magnet, say I have prepared some atom or some electron in some state, let's say psi equals to 0 plus 1 by root 2. This is a normal superposition state that quantum mechanics describes. So now, and so as you know, in the previous tutorial, I have seen that one of our colleagues, he has finally described this Stern-Gerlach apparatus and basic quantum mechanics. So I am assuming that you all know that what is happening inside the Stern-Gerlach magnets. So as you know, so let's say this spin up, which is given by this 0 gate, is going up. The detection on up direction, from the detection on the up direction, we say that this is a spin up state, and detection in the down direction, I say that it is a spin down state. The prepared state was in spin down state. So now in this state, which is written here, if I prepare thousands of electrons or lakhs of electrons, let's say I have prepared 10,000 electrons in this state, and I send one by one, and whatever, I mean, like after this 10,000 run, I will observe that half of the particle, means 5,000 will go up and 5,000 will go down, right? Maybe let's have the experimental, there are some experimental errors. So near about 5,000 will go up and 5,000 will go down. So what is different in this scenario from the previous coin toss experiment? So now if I ask you that, let's say this is happening. So half of the particle is going up and half of the particle is going down. But I am providing you an ensemble of particles, like 10,000 particles. Let's say I have given you one single electron, and I say, I have given you this electron. This state is this electron state is this psi, which is provided by the quantum mechanical prescription, like this superposition state. I have provided you. Just believe in me that it is in superposition state. So if I ask you that now send this electron to the Stern-Gerlach magnet and predict with some equation or whatever you may have in your surroundings, you just predict where the electron will go. So can you predict that?
Sir? Hello.
Hello.
Yes, sir. So by calculating its expectation value, since we are doing this particular experiment on the ensembles all over the.
No. Just understand my question. Previously, it was like an ensemble of electrons. Now I have provided you one single electron. Okay.
Okay.
So then with that single electron, I ask you send it through the Stern-Gerlach magnet and predict where this electron will go up or down. So can you do that with some kind of prescription, some mathematical or physical?
Like repeatedly, we need to do the experiment on that particular single electron.
So single electron, after the detection, that single electron, how can you get after one detection? So I have given you only one electron, not many electrons. Like many electrons in the same state, I have there is no provision, say, in that experiment. So there is no provision of creating many electrons of the same state. Let's say you have only one electron. Like you have given one single coin. There is no other coin. So with Newtonian laws and by Lagrangian formulation, you can just equation of motion, calculate the equation of motion, and you can predict.
In that case, we need to study its dynamics. So
yeah, can you do that? Can you do that? Like by studying any dynamics, can you predict where the electron will go? Is there any dynamics?
yes, sir, I can try.
Yeah. So let's say now by the time you try, let me also try. Okay. So from this presentation view, I am now going to some let's say paperwork. So here I am also trying. So let's say so this example, let's say there exists something like, so only providing wave function, by providing wave function you can actually predict the outcome of something. So let's say we are doing that. So this was given by Einstein. This is a very simple example. You all know about EPR argument of 1935. But even before that, and that actually contains some peculiar kind of state called the entangled state and this kind of things. So let's not go into that complexity. Let's stick to the superposition principle only. Can we say something about this wave vector? This question that I have raised.
I'll just make a small comment here.
Yeah.
So I think what your question should be clear to everyone now, that can we predict the exact measurement results of a single measurement?
Right.
Isn't it?
Yes.
So for each particular experimental run, can I exactly anticipate?
Yes.
Yeah, but that is the question he's asking, that can we do that? Like, for example, in classical mechanics, we can, if you have all the preconditions, we can do that. But for quantum, can we do that? That is the question you are asking, right?
Yes, right.
So, but quantum, yeah, so it just gives probability, so we cannot get any predictable.
So quantum theory is a theory that explains the statistical outcomes. Let's say it can have the limitation that it doesn't predict the single experiment results, but can there be something in nature, or can in principle it be possible to predict the outcome of single measurement? I think that is the question Sumita is asking.
Yes, exactly. So like in classical mechanics, just compared with your classical mechanics, say, let's say in your classical mechanics, what are the fundamental quantities that you are interested to predict the motion of some object or trajectory of some particle? So that is the position and momentum, right? In classical mechanics.
Yes, sir.
If you know position and momentum of a particle, and if you know the dynamics, then you can actually construct a phase space trajectory of that. Say this is x and this is p, right? So is it more visible now, the screen?
Yeah, it's okay. I mean, you can do in landscape or portrait. It's fine.
Portrait is maybe convenient to me. So okay, so classical mechanics, you have these variables. So I'm asking whether in quantum mechanics, can I introduce such a variable? Let it be, maybe it is psi. Psi is such a variable. It can occur. Let's say x and p, the corresponding quantity in quantum mechanics is psi. Can it be possible? Like I want from quantum mechanics, the statistical result is correct. Quantum mechanics is no way wrong. Like each experiment has been performed on the Earth in the microscopic level, that all actually reproduces the quantum mechanics bond rule. So quantum mechanics is anyway a correct theory. But I want from quantum mechanics not only the probabilistic nature. Like I not only want to describe the probabilities of certain outcome in an experiment, I also want that if individual experiment is being performed in lab, I can unambiguously predict event by event description of that particle through quantum mechanics, which classical mechanics has. Like if I provide X and P and some other parameters, you can do anything. You can predict anything in classical mechanics. So now let's say, okay, let's say psi, let's check whether psi provides such a description in quantum mechanics. Because psi is the fundamental thing in quantum mechanics. Psi gives the probability of certain outcome, right? In the textbook material we have read already. So let's say whether psi has this property to predict the outcome. So now for general, say Einstein had tried actually. So before EPR paper in 1927 Solvay conference, Einstein gave certain arguments on this, whether quantum mechanical description given by wave function is a complete description of reality. Reality means what exists, let's say for simplicity, let's say what exists even without our observation. Like, so let's say such variable exists, okay, and such variable is given by this lambda psi t, okay. So this is argument given by Einstein, as I previously said, okay. So this is I think it is a simpler argument than EPR paper. So let's say here is a hemispherical photographic plate which can detect electromagnetic radiation, and here is a slit, a aperture from which electromagnetic radiation can come in and can be detected into the hemispherical surface. And let's say for simplicity, just for simplicity, there are 2 points A and B. So now I am writing the wave function of the particle. Let's say this psi is given by A plus B by root 2. What that mean? That means, let's say there is only 2 possibilities of detection. Like either it will be detected at A or will be detected at B in that hemispherical surface. You may have multiple number of measurement result also, but for simplicity, I am just taking two measurement results. So let's say there are 2 states. If it is detected at A, it will be Ket A, and if it is detected at B, it will be Ket B. And the state of the electromagnetic radiation or whatever photon, let's say, it is A plus B by root 2. Okay, so normal superposition from quantum mechanics. So now a measurement is done. As you know, that measurement is actually what? Convex combination of, I mean, like this spectral decomposition of this projector, right? B. Let's say I denote it by pi A and denote it by pi B, right? So now, what is the probability that quantum mechanics predict of the event A? What is the probability? It is a statistical observable probability, okay? Like one in the Stern-Gallagher magnet. So PA, this is simply the Stern-Gallagher one. Like you can replace this experiment in a Stern-Gallagher magnet. But I am conveying the same example that Einstein has given in that argument. So what is the probability of it? Can you say? Just someone say, like someone tell me what will be the probability? Of the event A. Hello? Hello? Hello?
One student says half.
Huh?
One student is saying half, and
Oh,
that is
okay.
in the chat. We don't have any more answers.
Okay. How did you get this result? Like half? Can you say?
I mean, anyone can unmute themselves and
Yeah,
like interact
anyone can.
directly to the speaker. I think he's not, because he's sharing the screen, he's not been able to reading the chat.
Yes, exactly. So can anyone say?
He's saying coefficient square in front of A, the square of probability amplitude.
Yes, right. So actually this is coming from the bond rule, right? Probability of
Yeah.
certain outcome.
Yeah.
So this is, you can write it like, say, psi and pi a, right? Or maybe if I don't use this notation, this is just psi and this a mod square, right? This is simply half. So whoever answered the question, it's right. So like, it's half. Now let's go. I get the A outcome. So now I am calculating this probability AB. What is the probability that I get A and B simultaneously? Detection at A and B simultaneously from a single photon. Let's say one single photon is going there. So what is this joint probability? So this will also be calculated through the bond rules. But so in normal probability, I can use this Bayes formula, right? So probability of a joint event A and B is probability of A and probability of B given A, right? The product of these two terms. Is there any confusion?
Hi, Sumit. I have a
Yeah.
little bit of confusion.
Yeah.
So that is from a single photon and a single shot experiment, how can you get a simultaneous outcome of A and B?
That is I am asking that anyway, mathematically I can calculate this probability, right? The simultaneous detection. So whether it will happen or not, that depends upon the certain experiment or certain theory.
Okay.
So in general, I can calculate, right?
Yeah,
so
in general, mathematically, you can process.
Mathematically, I can just take that.
Yeah, and
so
let's
probability of A, I calculated half, right? Previously, I calculated probability of A half. There is no doubt of this. Now this probability of B given A. So if A outcome occurred, what is the probability B will also occur? So what quantum mechanics predict? If A outcome occurred, so the state will be reduced to this one, right? If A outcome occur, reduced to this one, right? Just by using quantum mechanical prescription. So then my state will become this one. So now what, and my projector corresponding to B is what? Pi B. And if I say, let's say AA, this, because my state is now AA, right? So what will be that? This probability is simply 0 because A and B are orthogonal, right?
Yes.
So that means in quantum mechanics predicts that probability of getting simultaneous detection at A and B is simply 0. That you are talking about. Yes. So now let's say that, okay, so quantum mechanics is predicting this. And this is a right prediction. So now let's say a variable exists, such variable which I was talking about previously, that gives event by event description, not the probability. So let's say that variable exists, and that variable is actually nothing but psi. So psi is giving that description of that variable, like x and p, those kind of thing in classical mechanics. So that variable, now here I am denoting by this lambda. This is famously, people say this is a hidden variable because we don't know anything about this variable. We are just constructing a mathematical model to extract some property of this variable. That is why it is called a hidden variable. So let's say that exists. So now I am calculating the same probability again, PAB, in that theory where this variable exists. So what will be that? Let's say I denote this probability by P lambda inside. So it will be A lambda and then P of B lambda. Only I have introduced a new parameter, say called lambda, right? Let's write it in this way. Okay, only. Am I right? Can I write this one? Just I am assume that A is a function of lambda. Then can I write that? The
Yes.
outcome is function of lambda. So likewise, we write like E is a function of something called angular momentum or something like that. Just simply like this. In classical mechanics, like we write. So say some observable quantity is a function of x and p. Similarly, I can write this, right? So now I am assuming another important thing. So this is very important. So let's say I am assuming something you may have heard, locality condition. What is that? Don't go into the very sophisticated things of locality, this Bayes theorem and all. Just for like simple, just understand in a naive sense. Like my picture was this one, A and B. So probability that this B due to A, given that there is a lambda present there, is simply P of B lambda. This is I am assuming my locality. What is that? Because why it is locality? Because this effect of B is only because the outcome B cannot be come from A. So B cannot be a function of A. Just understand like this. So like whatever happened at A, it cannot influence the probability of B. So this is simply this, right? In the present of lambda. That in that theory I am discussing it, not in quantum mechanics now. In that theory, in the presence of lambda, the outcome of B is not dependent on what is going on at A. So this is my locality. Now assume this. So is there any confusion? So because this is crucial here. Hello? Am I audible?
Yeah, Sumit is asking, can you explain it again?
Okay. So let's say so just consider this picture. So one photon is going in, like I have written the state and all. But the locality, what I am assuming, that a detection at B, this is what? This probability of B given A lambda is what? Probability that a detection at the point B occurred, given you have a lambda and A has clicked already, right? This is this probability. So I am saying, I'm assuming, in general, I cannot assume this. If I am assuming this, I have to give a name. This is an assumption. So I am saying that this assumption is a locality assumption. What is that? That this is equivalent to B, writing B lambda only. So B is only a function of the lambda, that hidden parameter, and it do not depend on whether A clicked or not. So it is not a function of what is going on at point A. So is it understandable? So this is my assumption, one assumption. I say it is locality. Is it
Yeah,
understandable?
I think you can proceed. He says yes.
Okay.
Sumit, one more thing. can you tell me if that assumption, if you are not considering that assumption, then what may be the consequence of it? Let's say if it violates that condition, that probability of B condition on lambda A is equal to probability of B condition on lambda. That means probability of B is independent of A. If that violates, what kind of consequence will happen? Can you
Yeah,
tell us little bit?
that is a very interesting question. If it is violated, so let us go from the back direction. Let us assume and see what consequence I have.
Okay. So later, I think you should tell more.
Okay, yes, surely.
Yeah.
So for now, I am assuming this. Okay. So now my this probability, now it became, so probability of AB, it now became what? P of A given lambda and P of B given lambda, right? This probability, this become this. So
Will
now
it not be times P of lambda?
P of?
P of lambda times P of A became,
No,
is it right?
because no, I'm saying that, let's say this is lambda. Lambda is already given. So yeah,
Okay.
I have written something. So let's say this one conditional lambda. Okay.
By the one thing I must mention, you don't go beyond that line, because then it will not be streamed in YouTube. YouTube screen is somehow cropping your screen. So that is the limit that you have. Yeah.
Okay. So I can move to next page, right?
Yeah.
So let me write the same thing over again. Let's say AB given lambda, or I may write lambda in the suffix also. Let's write it like this: P of A lambda and P of B lambda. Okay. So now I am applying quantum statistics. Okay. So let's say lambda. Now I have assumed that this lambda is a variable which is equivalent to psi. Means psi is giving those description, event by event description. Let me assume this. This is also an assumption that psi is this lambda is equivalent to psi. Let me assume it. So this is another assumption. So I have now two assumptions. One is that locality, and another is psi is giving the complete description. So psi is that parameter lambda. So now I can write what? AB lambda equals to P A psi P of B psi, right? Is it right? I just replace lambda by psi.
Yes.
So now you calculate from our previous equations here, from this state, calculate PA. Already we have calculated PA is half, and similarly PB is also half, right? PA we have already calculated. So given lambda we have introduced, like this is the state of the system, which is half, right? And second is also half, right? If lambda gives if lambda is that parameter which gives event by event description, and also what lambda property is given by quantum mechanics, that is intact there. And I am claiming an extra thing like lambda, the psi also gives that event by event description, which should be given by this parameter, hidden variable parameter. I'm actually demanding from psi this extra thing. If I impose that, I just impose these two things, right? Along with locality. So I have two assumptions, locality and psi is that parameter. So what I get, it is 1/4, right?
Yeah.
But previously what I was getting?
0.
This one, right? This one, 0, right? So see, this is the apparent contradiction even inside quantum mechanics. If I assume that the quantum mechanical wave functions gives the event by event description of certain things, right? Some parameter. If I assume, let's say not go into that size giving some event by event description, even if I allow like the weak assumption, like psi is equivalent to this parameter lambda, whose properties I don't know, then inside quantum mechanics there is something, some contradiction. So as Saurodipda was saying, if I don't assume this locality, so then what in this scenario what will happen? I cannot show this contradiction, because if there was no locality, there would be this term, right? PBA lambda. So this kind of contradiction, then I cannot show here. So that is the only thing. That means what? So locality plus, if I say psi lambda, I say that psi is lambda. So this is one assumption. And this implies quantum statistics is violated, negation of quantum statistics, right? So this is very simpler argument. So this is do not require that peculiar state called entangled state, which is used in EPR paper for their argument of like that quantum is the same argument, but it's a more defined argument there. But my argument here is that even without that kind of peculiar state, you can discard certain kind of models where psi represent that parameter, that hidden parameter. Psi directly represent that. Only those kind of model is discarded here, not other models. I can consider some other peculiar model, but at least this model is discarded if I assume locality assumption.
There is a question though.
Please.
Yeah,
You can actually unmute. I mean, whoever is asking, just directly can ask.
Yeah, his mic is apparently not working. He's asking to explain the physical implication associated with the outcome. What is the physical implication if you, I think what he means is if you associate psi with lambda, what is the physical implication of it?
Yeah, that is this implication, this bracketed thing. Like I assume locality, I cannot say single-handedly if lambda is psi, something is violated. But if I assume an extra assumption called locality and this assumption together, showing a contradiction with quantum statistics.
So that means to me, so quantum statistics is correct, because there are infinite number of experiments has already been done, and they confirm that quantum statistics is correct. So that means either whatever your locality condition, either it is not true or psi cannot be the complete description of the system.
Right. Exactly.
Psi cannot provide the event by event description, just like the classical variable x and p.
Right.
You are kind of. So one thing I want to add, that whatever you are telling that locality, it is actually outcome independence. I think that's more less confusing thing, because locality you always
always outcome independence.
Bell type of locality, but what you are taking, they are the outcome independence. That
right. Here you can actually say this term is outcome independence, because locality term was not coined till then when this argument was given by Einstein. So that was like an assumption. So I just use this locality, like it is confusing actually. So usually for Bell's theorem, their outcome independence and setting independence are there. So conjunction of both these things gives this locality assumption.
Yes.
So, but say this is something like Einstein's locality. Let's say E locality here, or outcome independence, whatever you can think. So actually, in this field, terminology are more interchangeably coined that people gets confused.
One thing again, that what do you think that which is more natural to violate? I mean, in our classical point of view, psi may be a complete description. Then if we violate that locality assumption or the instant locality assumption, is it natural or unnatural to violate that assumption? I mean, natural means classical point of view, in the classical perspective.
So, so it's like a question. Personally, what I think, like, as I know already Bayes' theorem, so I will go with the past. So,
Okay.
but yeah, for now.
Okay.
So, but my mind said that this is second thing is also possible. So, what do you think?
No, that I don't know, and that I just ask you that for the larger audience, that because people are asking that what should be like physical implications of the of that kind of assumptions and all that. So that's why just I want.
And also one thing is crucial here. Say I have assumed, like, strictly stick to this assumption. Like I have assumed lambda is equivalent to psi, right? I mean all the parameter which is giving the reality is converges to psi.
Yes.
Not other things. Like there can be this thing also. Like say there are certain parameters lambda 1 and lambda 2. So let's say lambda 1 is psi, but there is some extra lambda 2 which is also giving the description of reality. That can also occur. So I have not discarded that model.
Yes. Nice.
Right. So people actually in literature, they say this is a psi complete model. Speckens and all these guys actually say this is a psi complete model where psi is all. I mean, psi is giving this reality description. There is no other parameter. So this is called psi complete model. So let me, for the audience also, let me write this terminology. They can find it easily then.
Don't write it there. Write it in the next page.
Okay. Yeah, I forgot. Yeah. So this is psi complete model.
So if you violate actually outcome independence, it means that what does it mean physically? It means that
so either if you let's say you assume, or it is true that quantum mechanical statistics is true. So there is no way you can say that there is a negation of quantum statistics. So either of these two assumptions is violated. So outcome independence, so let's say first one is violated. This outcome independence or Einstein locality, whatever it is violated. That means in that theory, which is giving this event by event description of certain events, in that theory, the probability of A is influenced by probability of B is influenced by probability of A, which is occurring at a distant position, right? So Einstein,
but I think the spirit of the question was that if it violates, then whether it violates any other physical principle or not. Because if outcome independence violate, it will not violate no signaling principle. So
surely, yes.
It will not violate no signaling principle. Okay. So I think we can always assume that, okay, in nature, maybe outcome independence can be violated because it is not creating any conflict with other physical principles.
Right.
Because you cannot send any message by violating outcome independence. That's why no signaling will not violate, right?
Yes. So here we are considering this lambda level theory. Like for individual lambda, this probability is like this. But when you sum up over all these things, you will get observable probabilities. So that are actually not violated. Like that is no signaling one. So if you extrapolate it to probability level, observable probability level. So no signaling is not anyway violated, but locality you can violate. The locality or outcome independence. So first one is this, and second one is this: if you like want to interact your locality condition, then the second thing must be violated. So then you can discard one certain model where psi represent all the parameters which is governing the reality. Okay, is it clear?
Yeah.
So just you can give a search in internet. So what this model, this certain model is termed as high complete model by some physicists. So now again come back to the slides where we were. Okay. Is it visible?
No.
The slide? No, right? Now maybe.
Yeah. Make it landscape.
Yes. Yeah. So I was here. So I was trying to construct such a model. So while trying to do so, I saw that certain kind of model cannot exist, at least, right? In this scenario. So let's see other kind of model can exist or not. So these are some views about reality by some famous physicists like Einstein. So Einstein says in the EPR paper, he says, what is reality? Like, you can have your own description of reality. So what model I am predicting, that ontological model, which is the title of this tutorial, this ontological model should reconcile with the description of reality, and also it should reproduce quantum mechanical result, because it is anyway lab tested result and it is correct. We demand it. So we demand from our ontological model those two things. It will actually reconcile with reality and also reproduce quantum prediction. So Einstein gave his view about reality. So he gave a definition of reality. What is that? That let's say you have two particles. I mean, you have two events. So he says exactly what he says, that if without in any way disturbing a system, if you can predict with certainty the outcome of a physical quantity, then there exists an element of reality corresponding to this physical quantity. That means what? So just like see all these words used in this statement. So like, so you have a system. Even if you can measure certain quantity of the system, let's say you have a ball and it has some property, like it is spherical and its color is, it can be red or blue or something like that, and you have a something like some other thing, say some dice. It is like cubical and it has some certain colors. So you want to measure one of them, like say take any of the example. So you want to measure the color of certain ball. So in physical world, I mean, in our everyday world, what happens? To measure the color of a ball, do we have to disturb the ball? Like, do you have to touch the ball or something like that? So by measurement, I am saying measurement is such a action which reveals some information about some quantity. This is my measurement, say. So if I give you a ball and I ask you the color of this ball, is it necessary to touch the ball? If you have an eye, if your eyes are actually not closed, is it needed?
No.
So actually, so this is like in our classical world. So this assumption about reality, this definition of, rather I will say definition, this definition of reality is coming from our everyday world. That if without disturbing, so the color of ball, you can just see that ball and you can say that this is red or blue or something like that. So this is your measurement. You are just observing it by your eyes. The photon is falling on that and photon is reflecting to your retina and you sense that. So this is your measurement. So this measurement do not disturb the system. At least we don't know like it is disturbing the system.
Actually, I think here maybe the disturbing means that the property doesn't change after the measurement.
Yes. Like it will be invariant after the measurement. Like it will be what it was before the measurement.
Yeah.
So this is our disturbance. So I am not disturbing the system. So I am just watching the ball. This is red. I will say that this is red. So this is my measurement.
Sumit, just one point. How you know that color measurement in classical domain is not actually affecting the property of the system? Maybe the ball was in different color, but when we see it is red.
Right. It is also an explanation. But people like I am not touching that ball. So in classical world, we generally refer disturbance like we are doing something with the ball, like we displace the ball or something like that.
So that means what you are trying to say, that if you measure any other quantity, let's say the shape or the position, then after that also, if you find the color of the ball is unchanged, then you can be sure about one thing, that okay, the ball had
to ensure that I have not disturbed the ball, I have to perform another method, like whether it is displaced or not. Right, absolutely. So it's this is for ensuring whether this is disturbed or not. So why we say that this ball
I have
has
a question, sir.
Yes, sure.
Yes, sir. Like sir told that in this ball, where we can observe one color, but it may have some other color also, which we don't measure when we observe the ball, right? But sir, the superposition principles does not work in macroscopic regime. So that the color of the ball, if it's red, it should be red, because the superposition principle doesn't hold in macroscopic regime, right, sir?
Yeah.
That
You are right, but actually I am not going into quantum mechanics. Just consider your classical view, what you know from your childhood by your observation.
No, sir. As sir told that if you are measuring the color red, suppose we are measuring the color red, but that sir told that the ball can also have some other color also. But if we measure, that's why we are getting red.
So
my question is the superposition principle. Yeah, my question is, like in quantum mechanics, we have superposition of things like ket of 0 and one of ket of 1, right? Two states simultaneously it can possess. Yeah, but in macroscopic regime, it is not the case.
Yes.
Yeah. So in microscopic regime, in quantum domain, a ball can have white and black color both simultaneously. Whenever we measure, we get one color.
Yes, you can say. But
but in macroscopic regime, there is no case like this. If a ball is red, it should be red because it cannot be in a superposition of red and blue.
Yeah. So we are not going to, let's say, we are not going to quantum mechanics. Say, forget about quantum mechanics. We don't know anything like superposition principle and all. Okay. So it is only after quantum mechanics was discovered, you say this superposition and all. Even before quantum mechanics was not there, let's say in 90s, there also this view was same. So if I measure color of certain thing, and then I can, without disturbing, can measure the color of the thing. And how will I ensure that this measuring of color has not disturbed the system? To do that, you have to perform another measurement, which Sorodipda was saying. So you have to ensure that, right? So to do that, you have to do another experiment. Like you have to measure the color or some position again, right? It is not even depend upon.
Here you can, here I think what you are trying to do is giving the perspective about what Einstein thought reality was, or his definition of reality. So Einstein's definition of Yeah, Einstein's definition of reality is that if without anyway disturbing the system, you can measure some property, then that
Right.
property is real. That property is reality.
Right. 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 It is exactly Einstein's definition, and it is a sufficient condition for reality, not necessary. Okay. You can give another definition of reality.
So for
That
the
is
real
not-
world, the color of a ball might be an element of reality, or it is a
Element of
real property of the ball.
Yes. 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 In classical world, with this definition, you can say that this then in classical world, the color of ball is a real element of reality. Element of
But
reality.
then we can say that the condition for those for the real measurements would be the system would be the paradigm to be deterministic. So for example, if we measure red, we are sure that the color before it was red was because in the classical regime at least it was because we know that it follows the deterministic principle. So we can say we can deduce from that even if we measure red and we don't know what it was before, we can sort of
No, I don't
sort of
think you should assume beforehand that the color
Hmm.
was red. You do the experiment again and again all the time. If all the time you see the color was red, you say the color of the ball was red. But let's say the ball had an LED light inside it, and that light changed, so the color is sometimes red, sometimes blue. Then you cannot say for
But-
sure what is the color of the ball.
No, but
Yeah.
then for the same ball, it's the same as the quantum measurements we make. We make one measurement, and then if we make another measurement in sufficiently less time, we get the same result. But that does not mean that what we measured at the what we measured in the first measurement was in fact the real state of
No, but
or at least the state of the or at least the quantum state of the object before that.
that's why Saurodip
What
said
what
that.
I'm trying to get at.
That's why Saurodip said no, that you should measure other properties as well. It may happen that it didn't disturb the color property, but the shape was distorted. So by measuring color, the ball was round shape, let's say previously, and now it has become a cube.
This
That
can
is
happen.
also
So to ensure that you have to perform another measure, right?
Okay.
So that is even true in classical mechanics. You don't have to consider quantum mechanics. So just inspired from these properties, Einstein had given this definition. So Saurabh, do you have anything to say?
No. You can proceed.
Okay. So this is Einstein's view. So if without disturbing a system, you can predict with certainty the outcome of certain physical quantity, then there exists a physical reality corresponding to the quantity. As Soumik was saying that then color is a physical reality. So yes, it is true indeed. So there is another view, Bell's view. So I am not quoting Bell's exact words, but this was from his paper. So if the results of individual measurement can be accounted by some parameter without changing the overall statistics of the theory, then such parameters corresponding to the reality. It is even a weaker assumption, so Einstein's reality is there will be Bell's reality already, because it is very weak. Even if Bell has not mentioned disturbing and these things, disturbing a system, he says that if results of individual measurement can be accounted by some parameter without changing the overall statistics. So overall statistics is same, but you can give explanation of individual outcomes. So this is Bell's view of reality. So then there exists a reality. There are some other views and many other views. So this research is going on in this topic, like there is macro realism and all, but I am not going into that. So it will take much time to discuss this. And this is very philosophical debate. This will be then. So let's go. So now I have discarded one model as I have shown in the paper. So now say there can be some other model. So let's say there are three types of models. So does psi, so what is the current status of psi? So does it directly correspond to the reality? So we have discarded this model already, right? The first one. But there are two remaining models. There can be, at least I can think of two other models. You can think some other models also. If you can, then you can just tell me if there is some other model in your mind. So let me tell these two models. So we have discarded a model where the state psi, quantum state psi, represent directly the reality. We have discarded it. The second possibility is what? That is, psi is not directly representing the reality, but psi is representing an aspect of reality. That can be possible, right? So while writing, that is why I said that just stick to exactly this assumption. Do not go otherwise. So it can also be possible, the first one, the second one, that psi is not directly representing reality, but it's representing an aspect of reality, or some properties of reality. And the third one is what? Third one is completely different. So psi is no way representing the reality. It is only representing our knowledge about reality. Okay. So let's say we are standing in a bus stand and one bus came. So we see the number of the bus and we already have knowledge. This number of bus come from this route. So we predict that this bus may have come from this route. So this is what? This is our knowledge about reality from our observation. Our knowledge is that observation. We watched that bus. So the bus may have come from other route that day. Maybe some jam or something was there. So my knowledge may or may not be true for that case. So it is our knowledge about reality. So you can consider it like that. So now I will go to these two models, whether this kind of model exists in nature. And before that, I want to convey some like how to construct such a model in a general model, whatever it is, like the three possible model. So whatever it is, how to construct a general model. So let us go again into the slide. So a general ontological model. So what is the demands? So there are two demands. Demand from ontological model. Okay. First demand is, this is very the first demand is that it should reconcile with the description of reality. Okay. So that means how in classical mechanics the definition of the quantities of x and p are there, which is giving, I mean, if I know x and p, I can calculate any quantity, energy or anything in classical mechanics. So like that quantity, there must be some quantity which is gives event by event description of system. So first demand is that. So there should exist parameter that gives event by event description of system. This is our first demand from that model. Second demand is what? Second demand is very precise because we know quantum mechanics is correct. So at the end of the day, in the observation level, whatever the theory is, whatever its properties, at the end of the day, the observational statistics given by the probability, observational probability, which is given by quantum mechanics, that should be reproduced, right? So then, second demand is quantum mechanical reproducibility. Okay. So a general ontological model would be like this. So with these two conditions in hand, we will construct a model. Then we can see what other property this model should have. So the basic quantities of this model. So like in quantum mechanics, a state is represented by wave function psi. So this is a preparation in quantum mechanics. So here also there will be some preparation. How I will represent it? By a general probability. Say this one. What is this symbol means? So usually I will use for preparation, I will use this mu symbol. This is a convenient symbol. When you will read some papers, I mean, you will not be confused if I introduce this this notation. So whenever I will use this preparation for the probability, instead of this p lambda psi p, I will use, instead of p, I will use this mu, right? And for the measurement related to some probability related to measurement, I will use this xi. Okay. So this is just take a note. So this is for preparation, and this is for measurement. So let us now define. So now my preparation is now defined. What is that? This one. So anyway, we are constructing an ontological model for quantum mechanics. So psi will be there. So when I prepare a system in the lab, so these terminologies should be noted. Okay. So I prepare a system, not a state. I prepare a system, and state is a state. This terminology is a property of a particular theory. I represent in a particular theory, I say that this is the state. So I prepare a system in lab physically, and that is represented in quantum mechanics by a wave function. That is its state. So psi is the state of the system which I have prepared. So in the ontological model, instead of psi, there will be some parameter lambda which I have said. So it should fulfill that first assumption and first demand. So whenever I prepare the system that is represented by a state psi, by a preparation procedure T, I can prepare the psi in various ways. So let's say with some preparation procedure I have prepared. So in the ontological model, there will be a lambda that is explaining this preparation. So a lambda distribution is created. So this lambda is not, even though I am writing one lambda, but this is a distribution of lambda. Let's say in lambda space, there is a distribution. This is I am writing a continuous distribution here. So this is a lambda distribution. So for a particular psi, many lambda can be created in this distribution. Okay, so many lambda can be there. So this is the probability that having a lambda, given that the preparation of some particle is represented by psi and preparation procedure P. So this is my preparation. This is
Sumit, so that means, if I understand correctly, that the preparation procedure is P, in which you are preparing your system in the lab. Now,
right.
The state of the system in quantum theory is psi, and state of the system in ontological model is lambda.
Lambda, right.
Now, what is that probability distribution again? Represents the mu of lambda condition psi P. What that probability distribution represents?
Oh, that represent, actually there can be not one lambda. So lambda has a distribution, like I don't know these two axis properties. Okay. So there may be some hidden properties there. So let's say this lambda is represented in that dimensional space. Okay. I am not attributing any property to the lambda. So let's say there is some, maybe lambda is a vector or maybe a scalar. Right, so let's say in some space, the lambda distribution is created. So there can be many lambda. So this is that.
Okay.
So this is my now preparation. So preparation is now.
What is mu lambda?
Oh, that is mu lambda is a probability that in that getting one lambda, this lambda, say lambda star. Better I lay say a particular lambda star. The mu lambda star psi p is the probability of getting lambda star in the ontological model when my preparation procedure was P, and in quantum mechanics, this preparation procedure was given by psi. So this is that.
Achha, so that means with every preparation procedure, there is a possibility of preparing different lambda.
Different
With single psi or with different psi. Now you are choosing a very particular position that when lambda star is your state description in ontic model, and correspondingly psi is the state description in your quantum theory with that preparation P. So there must be some probability to consider this particular combination. So that that represents that particular combination, right?
Yes, that particular combination. Yes.
Yeah.
The probability of that particular combination. These three things.
I have a doubt. So you are saying that this P is a particular preparation, psi is a particular state in quantum mechanics.
Right.
And for these two values, preparation and state, I can have different hidden variable values lambda.
Right.
And this mu is actually the distribution of lambda depending upon for those two particular things, the state and the preparation.
Right. Given. That is given. So
Given.
I will tell you that my preparation procedure was this, and this preparation was represented in quantum mechanics by psi. Now in your ontological model, you prepare a lambda. So then you will write that, okay, this is my probability given those things, given those two things. Probability of a lambda given those two things.
So can I say that in this graph, the x-axis is lambda and the y-axis is mu lambda?
X-axis is lambda, one axis. That is one representation.
Is
you can give one such representation. One axis is lambda and another axis is mu lambda.
No,
but
the graph
here,
you drew here,
no,
is
it
like
not
for
that.
It is not that.
So you can construct another one where you are saying this is mu lambda. So you can construct. So I don't know what will be the probability, maybe a normal distribution. Okay. So you can also construct such a, but here my intention was to represent lambda in some space, like it can be a vector space or some scalar quantity can be lambda. So these axes I have represented from my classical intuition on it.
Okay, so what are the axes in the upper graph?
That is I am saying. So this axis, I am not saying anything about this axis, but what you have said, this one, the second one, you can have such a representation of lambda.
So what I was thinking is like for the particular preparation and the particular state, lambda can have different values, which I can represent in the x-axis, let's say. And mu of lambda given those two conditions is the probability distribution for that particular lambda value.
This is anyway right.
Yes, that is one way of putting it. And Sumita saying it is more general.
I am writing this. Yes. I am writing this. So lambda reside in some space, unknown space. Lambda reside in some unknown space. The first
Yeah. Hello.
Even I don't know this nature. I have written it like for generality, like some.
I have a question.
Yes.
Yeah. So like there would be different preparation procedures P, and there would be different states psi that we can assign to a system. So my question is the set of lambdas, that ontic models, is this set same for all the preparation procedures and like my state size, or for different state size for different preparation procedure, my set of lambdas will be different? Or is this
okay? So this is a possibility. What you are saying, that this set of lambda is different or same for same set of psi and p, right? If I understand your question rightly.
Yes.
So can there be different set of lambdas given one p and one psi?
Yes, to put it precisely, whether p psi lambda combination is unique or not.
No, so in general, it should not be unique. In general, when you are constructing a model, if you are assuming this, then this is an assumption.
Okay.
So the one particular ontic model can have this property. So I will go into that.
Okay.
Today itself, I will go into that.
Okay,
but there is a very good
someone is asking in the message that can you explain the distribution, please? What I don't know what distribution he is talking about. So maybe whoever is writing it, he can write it more elaborately.
Okay, so distribution space for I mean for the current use, you can assume the second one. This one you can assume. So this is like a probability distribution mu lambda for a lambda. So distribution space is this like this. So when I will consider some particular lambda, let's say it will be residing in some vector space, so then it will be a vector space. Let's say I consider lambda is a complex vector space, so it will lie in a complex vector space. So but for now I am not considering any properties of lambda.
So lambda can be a complex vector space, an element of complex vector space, but mu is the probabilities.
Mu is the
distribution.
probability.
They are the real values, right? They give
Yes,
real
they
values.
are the probabilities. They reside in probability space. Like so, what you are telling. Second one, the second example. So in x-axis you represent lambda, in y-axis you represent the probability of lambda given something. Okay. So now come to the measurement. It is preparation is now completed. So now come to the measurement. How measurement will be represented? So in quantum mechanics, how will you represent measurement? Can you say? Can anyone answer?
It's by POV.
Yes. So in quantum mechanics, you represent measurement by let's say by POV and some operator, Hermitian operators, right?
At semi-definite positive operator.
Semi-definite positive operators. Yes. So let's say in quantum mechanics, you have some measurement. Like my preparation, there was some measurement. So that measurement is represented by, in quantum mechanics, you have said that it is represented by some POVM element. So it is a POVM element, and in quantum mechanics, it should sum up to identity, right? Okay. So it is quantum mechanical description of a measurement. It is in general in quantum mechanics you can represent it. So in this ontological model, how will you represent it? So already preparation has been done. Only after preparation you are doing the measurement. Okay, you are doing the measurement on some preparation. Whenever you are doing some measurement, it is on some preparation or some system. So preparation is already done. That means lambda is already there in your theory, what you have constructed. So it is the effect should reveal some information given the lambda, right? Given the preparation. So now your effect would be something like that. So let us here write in K lambda M, right? So effect should be like this. So this measurement has done. This preparation was there. What is the probability that I get kth outcome? This is given by this response function. This is called response function in the ontological model. Is it clear?
So that means after preparing the system with preparation capital P, in your ontic model, the state of the system is lambda. Now you are measuring capital M on that lambda state. You are considering ontic theory. Then you will observe the K outcome.
Right.
So this response function determines the outcome
probability.
K, probability of obtaining outcome K.
Right. So and if this probability is positive, I assume this probability to be positive, then this is true, right? Right? Yeah. Because all measurement should give a result. At least one of them should give a result, certain result. So from that physics it is coming. So now consider a observable probability. How will I do that? So before that, let's consider this. If I integrate this preparation over all the lambda, what it will give? It will give you 1, right? Because for any preparation, psi and p, I assume that there will be a lambda parameter in the ontological model. There must be a ontological model parameter. So that physics is giving this normalization condition.
Sumit, can you give an example that if this is classical mechanics, then what should be the value of response function, or what kind of thing is mu? Can you give an example?
That is so like in classical mechanics, what we write, like say 3-dimensional probability space where this is represent px, py, pz. These are the momentum space I am writing. So in that space, the probability will be something like this. Let's say p dp and say p. So then it must, if the particle exists for which I am constructing this momentum distribution, if it is a dynamical characteristic of the particle, then it should be 1, right?
Yes.
So in the classical mechanics, I can just compare it like this.
Also, the response function should be 0 or 1, right?
Yeah,
Because
response function is 0, 1. Yeah, right. Because anyway, we have some laws which can unambiguously determine the state of the system. So we can always get that response function, we assume, in classical mechanics. Yes. So because that concept is in fact not there, that measurement reveals the value of something, some property. Even that concept was not there in classical mechanics.
Yes. So this ontic model is more general than classical mechanics, because their response function you are not taking as only 0 or 1. You are just taking it should be greater than 0, and
Greater than 0,
all
less
the
than.
outcome response should be 1.
Right. So it is, I should write it lambda n. It is greater than equal to 0, even it can be 0. So right. So now let me the observable probability now. So now I have 2 events. So I am erasing this one. Or it could be there also. So
there is a question in message box that can you suggest any books associated with this model?
Yeah, not a book, but I can suggest some papers. So at the end of the this tutorial, you can stay there. So I will suggest some references, some books or some papers.
Okay.
So just give me a reminder at the end of the talk if I forget. So now I am constructing the probability of observable statistics. Let's say how the observable statistics, or let's say 2 events, the joint probability of 2 events is written. So it is similar, right? Like say I have already written it previously when I was constructing the other model. P of A, and this is simple formula. A given B given A, right? So just compare it with that. So now my question is that now I prepare a state psi with a particular preparation procedure P. Now my events are 2. One is what is the probability that I get 1 lambda I, some lambda. Say this is 1 lambda, okay, in the space 1 lambda. I am not writing any indices, but assume this is 1 lambda. So first event is first event is I prepare this preparation. What is the probability of getting one lambda in my ontological model? This is the event one. Second event is I did a measurement M and my preparation was already there lambda. What is the probability that I get kth outcome? So these are, so kth outcome, getting kth outcome is the event. Getting one lambda is one event. So now let's calculate these probabilities. What is that? That I prepared a state psi and getting outcome some phi k. I'm now writing phi k. Okay, for simplicity. Phi k means like in quantum mechanics, you know, like phi k is some projector, some projector of some outcome. Okay, so I'm writing in terms of some state vector, just nothing else. So what is this joint probability? So now joint probability, how will I write? So not integration. So this probability will be, first probability is that one. What is the probability of getting one lambda given preparation P and K? And second probability is our xi, that is some phi k psi and lambda d lambda, right? Is this right? Is this right? Hello?
Yeah.
So in quantum mechanics, what is this probability? Quantum mechanics, you prepare a state psi. What is the probability of getting a detection at phi k detector? That is simply given by the bond rule, right? Psi phi k mod square, or you can also write this one psi. This is in, I'm not going into the detail, but this is in quantum mechanics represented by some density matrix. This is called density matrix, and this is given by some projector, right? This is represented by this in quantum mechanics, P psi phi k, right? So now I can then write, so our second demand should be fulfilled. Then quantum mechanical probability should be reproduced by this model. So now I can write mu lambda psi phi k psi lambda d lambda equal to psi phi k square, right? This is true, right? Is it understandable?
Yes.
Okay. Let me move on then. So now we have constructed a general ontological model. There was two demands. I have fulfilled two demands. So now we have a ontological model. This is fulfilling the second property and also fulfilling the first property. I should have some state. This, right? Now I will investigate some probability, some possible characteristics of these models. How this model can be. So someone has raised some question whether with a given set of psi and p, I can have same ontological distribution or different ontological distribution. So those questions will come when we consider the characteristic of a general ontological model. So quantum mechanics has a very peculiar property. Hello? Yeah, so quantum mechanics has a very peculiar property called the quantum reciprocity. Don't go into these complex terminologies, but just understand the physics. So people use this terminology to represent this physics. So I have used this one so that later on when you read papers, you will not be confused. What is this? So what is quantum reciprocity? That is, if you prepare a state psi, then it has two properties actually. Reciprocity actually is a combination of two properties that quantum mechanics possess. And they are very simple actually, you all know, but I am just reminding. So if you prepare a state psi, and if you have a measurement which contains a projector like this psi, so measurement is
start.
hello. Some noise is coming. So
Is someone saying something? Tomodeep? I think it was just a noise. Please continue.
yes. So measurement is then represented by something like this, right? Minus psi bar, right? A general measurement. So let's say I have prepared a state psi and I have a projector like this in some measurement. So the first assumption, and assumption now this is the property that is called the quantum certainty. That is that if I prepare such a state, then with certainty it will cross this projector psi. You can actually check, just write the Born rule. So this is psi. This is one, right? So this is the first property. Second property is that its converse is also true. That means psi is the only state that crosses this projector with certainty. See, this is a converse statement of the first one. First, I have said that psi will always pass the detector given by this projector psi. And second, I said that psi is the only state that crosses the projector, that is detected by the projector. So let us see whether I have constructed an ontological model, whether that model satisfies this property. So I have to satisfy this property, right? Because quantum mechanics anyway obeys this property, this quantum reciprocity. So I have a previous equation, this one I have constructed from the second demand. So let us write it again. Or for simplicity, I am just omitting M and P. Let us assume that all preparations of psi are equivalent, all measurement of outcome K are equivalent. Let us for now assume, because for our current discussion, it is not needed. So I am just omitting this P and M. So let us now write. So it is psi, and this is lambda, and this is K lambda, this, okay, d lambda, right, equals to, or better I should write this phi k. I was writing phi k previously, phi k. So it is just phi k mod square. Okay. So now first property, let us analyze the first property. That psi is the psi state always pass the projector psi. So now my outcome is, then I will represent phi k by psi, right? The same projector of quantum mechanics which I prepared. So I'm replacing it. Psi lambda d lambda equals to psi mod square. So in quantum mechanics, what is this? This is 1. So I can write this is 1. This gives a very interesting property of the ontological model. See, previously you have one equation. This is now your current equation is this. But you have a previous equation. What is that? Mu lambda psi d lambda equals to 1, right? It was our basic requirement of the this ontological model. So together we have to satisfy these two equations. What properties? So to satisfy these two equations, what properties of mu and psi xi is coming from here? Can anyone answer this question? Just a mathematical question, nothing else. To satisfy these two equations, let's say I satisfy these two equations, what properties of mu and xi you can extract from here by satisfying these two equations? Just let's try to answer this question. This is interesting.
Might be the response functions, yeah, are deterministic in nature. So,
Yeah, what do you mean by deterministic?
like if we go by simple mathematics, the xi should be 1. So
now, in what condition xi should be 1? You have to satisfy both these equations. Yeah, you are, I mean, around actually. Just think a little bit more. So you are around. In specific, what condition xi should be 1?
when lambda is equal to psi, so
let me give you a hint. So for what mu, xi should be 1? For what value of mu, xi should be 1? Anyone else?
Like it should be delta, chronicle delta.
Which one is chronicle delta? Hello?
Sir, xi is delta lambda psi is the
Okay, so let me answer them. So see these two equations. What this equation means?
Sumit, I mean, they are right because the lambda equal to psi is also a hidden variable model, but such a hidden variable model is nothing but quantum theory. So we are not talking about quantum theory. Yeah.
No. That hidden variable model is not quantum theory. We have already discarded that model.
Yeah. So I mean, they're asking that whether lambda equal to psi, whether this model will reproduce this is or not. It will definitely reproduce.
Yes. So what I am asking them? So what is the so one of them has said that xi should be 1. So I'm saying for what property of mu xi should be 1?
Yeah, that's
this
a question.
But, yes.
Yeah. Okay.
Yes,
go ahead.
Yes. So see the second. Hello.
sir. Could I say one?
Yes, sure.
Sir, is the orthogonality property is
Orthogonality property in ontological models.
between psi and lambda?
Psi
So-
and lambda. So
from-
psi reside in different space and lambda is in different space. So orthogonality property you can actually say in some specific space, right? So two different quantities are orthogonal. That is in you can compare in same space quantities. So psi lies in Hilbert space and lambda is some peculiar different space. So not that.
Okay,
So
okay,
but look at this equation, second equation. Mu lambda psi, mu lambda psi. D lambda equals to 1. That means, so it is a continuous distribution. So if I write this like this, let's say this is discrete distribution, not integration. I am using summation, let's say.
Yeah, this is better.
So this is say mu I psi. This is I equals to 1. Okay. So let's say there are 5 lambda in the lambda space. Okay. So what will be this equation? Lambda 1 psi plus mu lambda 2 psi plus mu lambda 3 psi plus mu lambda 4 psi plus mu lambda 5 psi. Right? It will be equal to 1. So what so among these 5 terms, which will contribute to this 1, whoever is positive, right? Or some value, has some value, maybe. So it is probability anyway, it will be 0 or positive. It cannot be a negative value. So whoever is contributing to give this 1, whoever is positive quantity. If one mu is 0, let's say this one is 0 and this one is 0, they cannot contribute to this 1, right? Only these 3 will contribute then. Okay. Am I right?
yes, sir.
Okay. Okay. Now come back to this equation, integration. So in this integration also this statement is true. Which lambda that gives this probability a positive value, that will only contribute to this 1, right? So from this, I can say from here that whenever this is positive, this should be 1. Whenever this is mu is lambda psi is positive, this is 1. Right? I cannot say anything about some mu for which mu lambda psi is 0. For this particular lambda, I cannot say anything about xi. I don't know what xi that would be. Because even for those mu, even if xi has some finite value, positive value, it will not contribute to the integral. Right? Xi can have some positive value in this case, where mu 0 has mu is 0.
For any lambda that is in the support of this mu, that
Yes.
for all those lambdas, this xi's value should be 1.
Exactly. So then represent this state by, these states by something. Then it will be convenient to proceed. Like say I represent this by, say this is the support of mu lambda psi. What is that? That is for all lambda for which mu lambda psi is greater than 0, strictly greater than 0. This is my support. I will represent this set by this lambda psi. Okay. And another thing was there that xi is 1. So I will represent that set by something, say by some, say it was say C psi, something like that. So this is for those case, I will represent it by psi lambda is 1. Lambda is 1. Okay. Or I will represent this. Is it understandable? So I am just using some symbols to proceed further, because unless I define some set quantities, then it will be inconvenient to proceed further. Though this is looking at some complex quantity, but don't go into their jargons. Just assume that this set lambda psi is a representative of those lambda for which mu gives a positive measure, positive probability, and lambda c psi is those lambda, contains those lambda for which this response function is giving a value 1. So from the previous equation, what conclusion we got, that is, whatever be in the support of lambda, that is this. What that means? That means that one I have already told you. So whenever this mu is greater than 0, xi should be 1. That means support of mu is a subset of xi. Xi is a larger space. Xi can have some positive values even when mu is 0, right? So xi is a larger space. But at least in this space where mu is 0, I can say xi is 1. But xi can have some other value, say 0.5, in some region where mu is 0. So you can just see this like this. So this is something like this. So this is this xi space, and this is this mu space, and this is xi space. Okay. And surely it will be a subset of support of that response function, because the response function should not be always 1. There can be different values. So like 0.5, 0.75, 0.2, anything greater than 0. So some more general will be if I write all the response functions. So that will be psi lambda. So this is my relation now. So from the reciprocity, I have used that term quantum reciprocity. So the first property was that psi we pass this detector psi with certainty. So just using that property, I have seen that in ontological models also this is true. The first property is true. That means the response is 1 always for which mu has a positive measure. I mean, whenever a positive mu is created, it will always pass that response xi psi lambda with certainty. Xi is giving certain response 1, 1, 1, 1 for all the positive quantities. But is the reverse true? That means mu is the only ontological state for which xi is giving response. That is not a priori clear, because we don't know. We cannot infer anything from these two integral, whether those are the only responses. There may have different other responses, as I told you earlier. So that means the reverse property is not satisfied in such ontological model. If you satisfy the first property of reciprocity, second property is not satisfied. When it will be satisfied? In those cases for which this is true, right? If it is true, then you can say, okay, so xi will, I mean, this xi function will give response only for these positive mu quantities, and there is no other xi. So it is equal to that set. So these two sets are same, actually same set. those lambda will contribute to xi also and mu also. But in general, this is not true. So the first property is satisfied and second is not.
So for deterministic ontological model, support is equal to 4, right?
Deterministic ontological model.
Hmm.
For deterministic ontological model, support equals to code, you say.
That you have written that.
No, determinism derives, Saurabh.
Acha,
Determinism is
acha.
derived here. Determinism is not imposed.
Yes.
Determinism is not imposed. I mean, if those are equal, then we can say that ontological model is
No,
No,
when they are equal, and that's the important thing.
when they are equal, then we can say.
So deterministic model means this one should be only 0 and 1, right?
Yeah. So determinism does not mean, determinism definitely means that, but determinism definitely does not mean that, but always this is when these supports are equal, then you can say it's deterministic.
Yes, right.
Okay.
The opposite.
Right. The opposite is not.
Opposite is not.
Yes. The opposite is not. Yes.
When this is equal, then you can say this is deterministic. But assuming determinism, you cannot construct this one maybe.
Yes.
Right. So yes, so this is till this thing. So let us now analyze another different property. So when I was explaining in my slides, so there was 3 types of model. First one I have already discarded, that is psi complete model. Second model was that where psi represent a aspect of reality. Okay. So in that model, I will not go today. I will go in the third model. So, but briefly, I can just say that what does it mean that psi represent a aspect of reality, not directly to the reality. That means psi is a representative of some lambda set. Let's say lambda s, it is in some lambda s. Psi is equivalent to this lambda, but there are other lambda, say some lambda o in lambda o that has no connection with psi. That means what? That means psi represent one aspect of reality, not the whole aspect of reality. There are other aspects of reality. So this is called psi incomplete model. Previous was psi complete model. And this is called psi incomplete model. Means psi giving some aspect of reality description of, but not all. So this Bell-Kochen-Specker model, that is a psi supplementary model, where there are other lambda, which has no connection with psi.
There is a question in the message box. Is here contextuality coming with determinism?
No. I have not. Maybe I have not coined this word till now. Because if I use those things, non-locality and contextuality, this discussion will be more complex. So that I am today trying to stick only to the ontological models. As long as
brief answer, because that is coming, because determinism is coming, Sauradip's question has come. So that's why the people are asking questions.
Yeah. So I can answer one.
In contextuality scenario, non-contextuality scenario, the determinism is assumed, is imposed to the model. Okay, here it is not imposed. Determinism is derived for a particular property.
Yes. So after some time, I will tell one result also that will be connected to contextuality. Once I state the epistemic model, then I will show some connection. So it is the second model what I was telling about in the slides. So this is psi incomplete model, where psi represents some aspect of reality, but I am not going into this model today. So you can just see from some papers, I will refer you one example or 2 example of some psi incomplete model. So Bell-Kochen-Specker model is a such example. Okay. Psi incomplete model. So I am going into another one, which has rich history of debates. That is called psi epistemic model, which is my last model of the slide, where I mentioned that psi do not represent the reality, but represent a particular aspect of our knowledge about reality. or our knowledge about reality. So psi represent our knowledge of reality. This model is popularly called psi epistemic model. Epistemic means our knowledge. And the first model where psi represent directly to the reality, that is famously also called psi-ontic model. Because ontic means being, that is what is there. This is not dependent upon your observation. So let us start this one. This one is very interesting, psi-epistemic model. So the question comes, where the question comes from, psi-epistemic model. So there is Hilbert space. Okay, so Hilbert space two state vector, say psi and phi, they have certain overlap in Hilbert space, right? So this overlap is accounted for by this one, right? Some quantity, some Q quantity. So people have asked a question that, okay, you are for quantum mechanics, you are constructing a ontological model. So whether the quantities that is representative of that ontological model can, from their overlap, I can infer the overlap of Hilbert space state vectors? This is the question. Because as you have seen that, so there can be two things, like say this is mu lambda. Okay, so mu lambda is not recognized.
Excuse me, sorry to interrupt. Can you please repeat that question?
So the question is that, so you have quantum mechanics where you represent a state by state vectors, psi, phi, etc. And you have now ontological model for quantum theory where you have this lambda parameter, which you infer from by observing your psi, right? When I have written this probability, I have write like this, right? So given psi, what is the probability of lambda? So people are now asking, so say you have produced two such things, lambda, phi and psi. So phi and psi are not recognized. No. So two such probability distribution. So whether they overlap in, or if they overlap, whether from the overlap I can infer the overlap in Hilbert space. So let's say I have two distribution over here. So this is first one, mu lambda psi, and this is mu lambda phi. Okay. So see, this is not overlapping. So from any lambda, if I give you one lambda, you can certainly say, okay, it is coming from this psi. And if I give you another lambda, you can say that, okay, it is not coming from psi, it is coming from phi. But a complex situation, let us consider, where this probability distribution overlaps. Okay. The same probabilities, this one and this one. So overlap. So from this region, this is the overlap. So from this region, if I give you some state by some lambda, you have to predict what will be the psi and phi. So this is the question. Can you predict the overlap? From this overlap, can you predict the overlap in this quantum level? So let us then write overlap into this theory. And one in ontological model, I will write the overlap quantity representing overlap, and I will also write the overlap quantity in quantum mechanics. Let's write. So it is previously also written in this tutorial. So what is the overlap between two states? This is lambda psi phi lambda d lambda is, in quantum mechanics, it is psi phi square, right? It is also previously written, the reproducibility condition, what we talked about. So I can divide it, right? Say I can divide it in two integral. One is this one, mu lambda psi lambda d lambda plus all other lambda that is not in this. So just remember, or I will make you remember what is lambda phi space. Lambda psi, nothing I am doing, just dividing this d lambda equal to psi phi square. Do you remember what is this space? Lambda phi. So lambda phi is that space for which mu of lambda phi is greater than 0, strictly greater than 0. That space is this one. Okay. So we had a conclusion previously. What is that? Can any of you say what is the conclusion? Whenever this is greater than 0, what will be our response function corresponding to it?
It will be 1.
Yes, it will be 1, right? So then at least in this space, I can write this response function to be 1, right? So let us write mu lambda psi in this region d lambda plus another quantity that is not there, mu psi lambda. In this space, I cannot write anything because till now I don't have any properties that I have discussed. What will happen in this space for this preparation or this response? I don't know any properties of this integral till now, right? So I am writing it as it is. So now this is equal to same psi phi square. So now understand what is this. So in the left hand side, this quantity, what is this quantity? This space is what? Where phi is positive preparation. I mean, the preparation of phi is positive, like mu is positive, right? That means a preparation is there in ontological space for this phi. It is that region. And mu psi, it is already that anyway that mu for which lambda and psi exist. So for psi it is the lambda. So this is then the overlap of ontological space of that two states. Do you agree with that? Or anyone have any disagreement? I am saying this quantity is ontological space overlap. This quantity. Will you agree with me?
Sumit, let maybe question can come that like this. You prepare lambda. So then mu lambda has a positive support in this mu. So it may not be possible, it may be the case, maybe it's that particular lambda does not respond to the phi.
That can possible. That can be possible.
So this is already 0. Those who are not giving any response to that, these Ji's values are already 0.
But okay, that whose Ji value is 0? Ji for phi or Ji for psi?
Ji for phi.
Okay. Okay. So you are considering one space where Ji is 0. Ji for phi is 0.
For example, I particularly prepare a lambda star for which this is in the space. This lambda star is in the space of this lambda phi. But for that particular lambda star,
the phi xi phi may not respond. Phi response function, I
Oh,
mean, the may
so
not respond.
for that case, this whole integral will be 0.
Why?
Because one of the quantity is 0. You are saying this is 0.
No. One of for a particular lambda.
Okay, for a particular lambda,
Hmm.
you are saying this xi quantity is 0.
Yeah.
So for that particular lambda, there this overlap quantity, it will not contribute. I mean,
Yes, it will not contribute. Yes.
it will not contribute because the whole integral will be 0. But in this space, is lambda phi, capital lambda phi, this space is for those lambda for which this phi has a positive preparation probability. So this quantity, this multiplication of this and integral over this space only, this gives the overlap between the ontological space corresponding to psi and phi.
Yeah.
But the other quantity
for lambda phi, all the lambda star, that will give the value, one value to this response function xi.
Yes.
In this particular space.
Yes, on this particular space. Because I have chosen this space like this.
Yeah. So the rest of the space we don't know.
Rest of the space I don't know. So now, okay. So this is the overlap.
Now you can use this less than equal to sign. So yeah.
So now I will use that because now I have this quantity too. So till now I have not able to use that less than equal to sign. When I remove this quantity, because it can be finite, right? Positive quantity.
Yes.
Can
It
be
can
positive.
be positive.
Positive quantity. So I don't know the properties of this. So, but general, I have to assume that it is a probability distribution. So it is a positive quantity in general. Then if I remove this, then the equation will become like A less than equal to what you are saying. So this phi mu lambda psi d lambda will be less than equal to psi phi square. Or better, you may use this like it is equal to something, equal to some function. Say, see, the second quantity I don't know, but at least I know that it is a function of psi and phi. Okay, because these two probability exist. So there I can write one quantity that is a function of psi and phi, depending on what this trade-off will be determined. Right? So depending on this function, this trade-off will be how less this ontological space overlap is from the Hilbert space overlap. That is determined by the second quantity. So it is, I represented it like this. So
value will be between 0 and 1.
From 0 to 1. F psi phi should be 0 to 1.
So the interesting question is now when it is 1.
When it is 1. So if it is 1, then I can write just equal to lambda psi d lambda equal to psi phi mod square. So that means Hilbert space overlap is equal to the ontological space overlap.
Yeah, that's the most important statement. Yes.
So we generally call this model to be a completely epistemic or maximally high epistemic model. Means the ontological model, from the overlap of ontological model, I can completely determine the Hilbert space overlap. So this is called psi epistemic model. So there are some results that you can check. So maximally psi epistemic model do not exist. So at least some results are there where people have shown above 3 dimension, or some recent result have also with some extra assumption they have shown that even in 2 dimension this psi epistemic model do not exist. So they have calculated it also, some like f psi phi, it is already there. F psi phi cannot be 1, not be 1 for dimension greater than 3. This is a very precise result. So you can
Then
check
from
this.
what happens to the reality, whether psi is a part of reality? What about that question?
Oh, that you are in the talk from the beginning.
No, then from here, what you can say about the whether psi is a function of psi is a part of reality or not? But that
Oh,
question.
so from here, as of my knowledge, so I can say that because previously I have already discarded the psi-ontic interpretation, and here people are also showing that maximally psi-epistemic model is not also possible. So now my stand is that psi may be a partial knowledge about this Hilbert space overlap can be partially accounted for by this ontological space overlap. Means it is psi epistemic but not maximally psi epistemic, or maybe the convex combination of psi epistemic and psi ontic.
Go back to the earlier pictures.
This one.
Yeah. From here, one important thing is that then you take a mu psi and mu phi. From here, from the first psi is a part of reality, right? Psi is a part of reality, right?
Yes. First one.
I want you to explain this one. That is, what is the difference between two pictures? And if you take maximally psi-epistemic model, there will be another picture below.
So what is the difference? That means say our goal was to find one ontological model where there will be some parameter which determines event by event description of the system. So if I don't have this overlap, then that means for every lambda there will be a quantum state psi, right? That is unique. Means if I give you one lambda, that can come only from a particular psi, if there is no overlap between the lambda. But if there is overlap, then from just by observing the lambda, you cannot say whether it is lambda psi or phi. That means by observing psi and phi, you can only infer some information about lambda, not whole information. Previously, in the first picture, just if I give you psi and phi, you can always infer the reality because it has a one-to-one correspondence with psi, this whole space. But the latter case, you cannot do that. And the last example what I gave, for that case, this overlap is complete. Means it is fully overlapped. So these two ontological space is actually one. So all lambda residing into the ontological space correspond to both psi and phi. So this is that thing.
I have a question.
Yes.
Yeah.
Yes.
So like in this page only, in the second line, this integration of new lambda psi and xi of phi lambda d lambda. So in the previous derivation, this new lambda psi is greater than 0. Means only and with that comes with a condition xi of psi lambda is equal to 1. But here it is not psi, it is phi. So
yes. This question is expected. I was thinking that why you are not asking this one.
Yeah.
So if you are understanding this, this question should come in your mind.
Yes. Can you just
see here in this case, when I was explaining this one, first one, there was no phi, only psi was there. I was discussing only in terms of psi.
Yes.
No.
Yes.
Only discussing in terms of psi, I took this quantity like this simultaneous satisfaction of this two equation gives me that whenever, so let me write it, whenever mu lambda psi greater than 0, you have xi psi lambda equal to 1, right?
Right.
So this space actually I considered capital lambda psi, right?
Yes. Right.
But now see here this space is lambda phi, not psi.
Okay.
So that I can write it, right? It is not, I am not writing lambda psi space, it is. So in lambda phi space, this quantity is 1, right? That is what I have proved.
Yes.
So that is why I am writing it 1. If I would have considered this quantity instead of this, I could not write this one because I don't know. If I would have written this, then I could only write xi psi lambda is 1, not xi phi lambda is 1, right?
Yeah, and now I get it.
Now you are getting it.
Yeah.
Yes. Good question. Good. So this is some results. So maybe I am going out of time. So I have some other things, but I have already gone out of time. So
Yeah, so we think that
yeah,
we may need another session to
another
discuss,
session we discuss.
discuss the remaining things.
Today we have discussed the basic things. I have not gone into some other complicated things. So with this knowledge, we can come back in some other session to discuss some more things.
Yeah, and we'll schedule that later. We now cannot say for sure which slot will be. Like we have to see that.
So before finishing it, so let me give some papers that they were actually asking.
Yeah, and if possible, can you please quickly summarize the things that you talked about today?
Yeah.
It may be useful for all the participants.
Yeah. So first thing what I have talked about, that tried to construct a realist model. What you are trying to construct. So we saw that there can have possibility of 3 kind of model. So we have discarded one model that is called psi complete. Psi complete model is discarded. Third thing is that we have gone through the Einstein's Geneva Solvay conference argument about the incompleteness of quantum theory. So
Are you speaking anything? Because we cannot hear you. क्या हुआ है? कैसे? खत्म कैसे हो गई? आवाज तो नहीं आ रहा है।
Sumit, are you there? Hello.
Yeah, yeah. No, I
Sure,
cannot hear Sumit.
I think he got disconnected maybe. Uh,
I think Sumit is disconnected or there is some technical problem. So probably we should end the session here today, and we'll share the notes to all the participants if they need, or we may upload it to the website. You'll get there. So today there is no more activities. Tomorrow we have from 10 a.m. Indian Standard Time, we have the regular sessions of QIQT 2023. So we have 5 sessions tomorrow from 10 to 1 and then from 3 to 5. We thank all the participants for your kind attention. We'll email you about the next tutorial when it will be there. Someone is asking, what is the link? The Zoom link is same for every meeting. So you can actually join the meetings using the same link. Are there any more questions? Oh, the website. Okay. So this is the link of our website. You can access all the details. We still haven't uploaded any slides or any documents there, but we will soon. So you'll be able to access all the notes from this website.
So is there any question? So I was offline actually for some internet interruption.
Oh no, yeah.
Okay.
No, we actually we thought we should end the session. But anyway, you can just briefly mention what is left for the next session.
Oh,
And you
okay.
can
So
turn
so
on
I
your
was
camera
not
as well.
there. So I was not there in the where I summarized the this.
You were there for some time, but then you were
Oh,
not.
I thought I was online. So maybe
No,
it
no.
was. So I gave the references also. So now I can just screen
No,
share. So
yeah. We said that we may share your notes in our website.
okay,
That
okay,
will
okay.
work. That will work
Yeah,
for
yeah,
us.
that will work. Yes, yes.
Okay.
Okay, thank you, thank you.
Yeah. So we are ending the session here now.
Yeah.
Also, participant, those who are not able to get the note, our session will be on YouTube channel. If you want to watch it, the tutorial session, you can go our YouTube channel.
Yeah, you can rewatch it anytime you like, any portion. Yeah. So thank you all. We are ending the session.